Hello, Honors Algebra 2. We're going to be looking at Edgenuity Section 9.4, Evaluating Logarithmic Expressions. We have a few objectives: to evaluate logarithmic expressions by converting between logarithmic and exponential form, to solve logarithmic equations by converting between logarithmic and exponential forms, and to evaluate common logs using a calculator. So let's look at our first problem. Given this equation, capital M equals the log or the common log of capital I over capital S, we want to do some stuff with that. And this equation shows us the magnitude of an earthquake, like a 7 or an 8 or things like that. I is the intensity of the earthquake. S is the intensity of a standard earthquake. And so we want to write an equation for the magnitude, M, of an earthquake 100 times more intense than a standard earthquake. And then figure out what the magnitude of that is. A standard earthquake is magnitude 1, okay? Or is intensity 1. I'm sorry, not magnitude, but intensity 1. Okay. So if we're doing this, then we have the magnitude equaling an earthquake 100 times more intense than a standard earthquake. So a standard earthquake would just have this. So we want to be 100 times that, right? A standard earthquake would just have, these would be the same. So we could call this the common log of 100 then, because if these are the same, they would equal 1. And so the way you do this is you get on your calculator and you usually turn it into a scientific calculator. You find the common log button, which is the LOG button, and put in 100, and the common log of 100 is 2, turns out. We'll see later why that is. But so an earthquake that is 100 times more intense than a standard earthquake would be a 2 on the Richter scale. The M is the magnitude on the Richter scale. I'll give you a moment to look at that. And let's look at our next problem. All right, let's rewrite this equation in logarithmic form. So the way that you do that is being able to write logarithmic form and read it carefully, okay? This number is the base, so it's log base 5 of something. And the something, it wouldn't make any sense for it to be the 3 because that's already there. So the something is what the exponential equation equals. So it's log base 5 of 125, and then it equals the exponent, 3. So every log equation is a question. What did I raise this number to get this number? And in this case, the answer is 3. So I'll give you a moment to look at that. And let's go on to our next question. Now we want to evaluate log base 3 of 81. So the way we're going to do that is we're going to say log base 3 of 81 equals some variable, let's say x. And we're going to go with the base 3. And what we're going to do is we're going to rewrite this in exponential form. So 3 raised to this power equals 81. So remember, this asks you a question. What did you raise this to get this? And that's exactly the question I've proposed here. What am I raising 3 to get 81? Okay? And this will be easier for us to do if we can write 81 as a power of 3. So, for instance, 3 squared is 9. 3 to the third would be times another 3 is 27. 3 to the fourth would be not times another 3, which turns out to be 81. So I can write this as 3 to the x equals 3 to the fourth, which means I can ignore the bases and set the exponents equal to each other, and I get that x equals 4. So that means that the log base 3 of 81 equals, remember we set it equal to x, so it equals 4. I'll let you look at that for a moment. All right, let's move on to the next one. Same idea here. We're going to take log base 5 of 1 over 25, set it equal to x, rewrite it in exponential form. The base is 5, the power is x, and it equals 1 over 25. Well, 25 is 5 squared, right? So this is like 5 to the x equals 1 over 5 to the second. But 1 over is the reciprocal of that, which means this is the same as 5 to the negative second. Then I can ignore the bases and have x equals negative 2, which means that log base 5 of 1 over 25 equals negative 2. I'll let you look at that for a moment. And let's move on to the next question. All right, let's do what we've been doing, write this in exponential form. So remember, if you read it carefully, this is easy. Log base x of 8 equals 3. That means the base is x, and I raised it to this power to get 8. All right, I'll give you a moment to look at that. Maybe rewrite this 3 so it looks a little bit better. And let's move on to the next problem. Excuse me. I'm going to take a little drink of water before I work on this problem. So let's look at how we would solve something like this. And as long as you have a log of the same base, and in this case, if you don't see a base, notice that on here we don't have a base written, that means the base is 10, okay? If you just see log with no base, the base is 10. But what's really important is that if you see the same log, same base on both sides, you can actually ignore the log and just write the other parts equal to each other. Just like bases, because it actually is all essentially the same thing. So I'm just going to set these two parts equal to each other and solve. Add 3x to both sides to get all the x's on the same side. I'll subtract 4 on both sides and have 5x equals 10. Divide by 5 and have x equals 2. Now, one of the things that you have to do when you do these is check and make sure that nothing inside of the logarithm comes out to 0 or negative, because those are impossible in logarithms. So if you look back at the top and plug in for 2, nothing comes out negative, nothing comes out 0, so you're okay. So I'll give you a moment to look at that. And let's look at the next problem. All right, so now this one says evaluate using a calculator. So on your calculator, you want to find the button that says log. And you want to hit that, and usually it'll bring up this, and you want to put in 37. And then it'll give you some sort of a decimal answer almost every time, unless you get real lucky. And you just put the decimal, and they'll probably tell you to how many decimal places. And this one is approximately 1 point. Let's just go to 2 decimal places, 5, 7. All right, I'll give you a moment to look at that. And let's look at our last problem. All right, so the brightness of a star, they represent that the brightness with capital M can be calculated using this equation. Capital M equals negative 2.78 times log of P minus 1.35, where P is the number of days required for the star to complete one cycle. That is, for the star to rotate until it gets into the same position. Okay? Calculate M for P equals 84 days. And again, this is the common log, so this is just kind of a plug-in thing, negative 2.78 times the common log of 84 minus 1.35. So let's do that part first on the calculator. Or, of course, you could do this on Desmos also. So the common log of 84, so negative 2.78 times, let's do this to 2 decimals, since they've done everything to 2 decimals, 1.92 minus 1.35, then we got to do the multiplication next. So positive times negative is negative, and then 2.78 times 1.92 is 5.34 when I round it to 2 decimal places, minus or plus negative 1.35. So if I do 5.34 plus 1.35, I get negative 6.69 equals M. And there is our brightness. I'll give you a moment to look at that. And thank you for listening today. I hope this has helped. Thank you.